recording. Okay, everybody.
Wait, you were recording?
No, of course I wasn't recording. Okay.
I was recording.
To go
All
back.
right, everybody. Okay, class. What we're going to go over today is we're going to look at some more examples of related rates problems. Okay, notes on related rates are online, so you can look them up. Over the weekend, you got that sheet that had the list as well as 2 practice problems. By the way, the solutions to those practice problems are online. Okay. Work today is to see more of these things, and we're going to see a particularly tough example of how a related rate problem works. Okay, one that would be a good one to follow along with. Okay, so the very first one, we're just going to follow along with the problems in the book. Hence why the camera's on over there, so you can see the problems. Okay, first one we're going to look at though is number 1, just to get an idea of how these things work. Actually, let's not do number 1. Let's do number 3. Okay, let's do number 3 instead. So, page 154. Okay, so number 3 we're going to do first. We've got xy is equal to 4. Okay, and what we want is we're going to differentiate this with respect to time. Okay, so our variable actually is going to be t that we're differentiating this with respect to. Now,
Is that
this
xy equals what? 4?
xy equals 4. Okay. Now we actually have 2 other things going on here. Okay. We have one problem A and one problem B here, kind of both. This is going to be what we want column and what we have. Okay. So for A, we want dy by dt, and what we have there, okay, is x is equal to 8 and dx by dt is equal to 10. Okay? In the second problem, okay, we want dx by dt. And in this one here, x is going to be equal to 1 and dy by dt is going to be equal to -6. Okay? Everyone got that so far? Okay, good. So, first thing we're going to do here is, since we want derivatives, we're going to take the derivative of this thing with respect to time. Okay? So, what rule ultimately am I going to use here? Because I got x times y. Going to use a product rule. Good. So, product rule says take the derivative of, keep the first thing the same, multiply it by the derivative of the second. So what's the derivative of y going to be?
dy by dt.
dy by dt. Good. We're going to add to that the second one kept the same times the derivative of the first one. What's the derivative of x going to be in this case? dx by dt. Good. Okay? And we're going to be equal to 0. Because the derivative of 4 is 0. Okay? In this case here. Alright. Now, let's see what we've got. Okay, so in A, we want to solve for dy by dt. We're given that x is equal to 8 and dx by dt is 10. But what do we have here that we don't have over here? Y, right? I'm missing what y is. Okay? I'm given y right here, but I'm not told what y is over here. Okay? So that seems to be a problem, right? Well, what it means we have to do is either do one of 2 things. Either figure out what y is, okay, or get rid of y by rewriting, by somehow getting it in terms of x. Okay, we could do either way. As someone has pointed out here, wait a minute, I got this nice equation right here, x times y is equal to 4. I know x is 8, so couldn't I put 8 into x there and solve for y? Absolutely, that's one way to do it. I'd come there and say, okay, 8 times y is equal to 4, so y then should be equal to 4 over 8, or 1/2, okay? That's one way I could do things. That works, right? Another way I could do things, though, to come up here and say, well, I have y up here, I want to get rid of y, so I'm going to get rid of y by going to my first equation and rewriting y in terms of x, okay? So I could take xy is equal to 4. I can divide x from both sides to get y is equal to 4 over x. And then, whenever I see a y in the equation, I can replace it with 4 over x. Okay? Either way, by the way, is acceptable. It will give you the same exact answer. Okay? But note that you could do it either way, okay? What I'm going to do is, so that way, because I'm going to be needing a y and doing b as well, I'm actually going to replace y with 4 over x, okay? Which is what I was given. So I'm going to rewrite this then as, I'm going to replace the x with the 8, so it's 8 times dy by dt, plus, instead of y, I'm going to make it 4 over x, which will be 4 over 8, times dx by dt, which is 10, which is equal to 0. And now, all I've got left is dy by dt to solve for, okay? So I'll go ahead and do that. This over here is going to be what? 5. So I'm going to have 8 times dy by dt plus 5 is equal to 0. So that gives me 8 dy by dt is equal to negative 5. So dy by dt then, in A, is equal to negative 5/8. Okay? Any questions on what I did there? Note too, if I had done it over here and solved for what y was, I got 1/2. Well, what's 4 over 8? 1/2, right? So if I had replaced it with the solution to it, I would have gotten the same answer. Okay? So notice both ways worked just fine. Okay? Do I need to actually do b, or do you get the idea now? Okay.
Speed up for a couple seconds.
Yeah. So with b, I could do the same thing. I can either use y is the fact that y is equal to 4 over x in b to solve for it, just using the new numbers, or I can replace up here. I could replace x with 1 and solve for y, get 4.
How is this problem shown in the book? Is that how it's shown? Like,
Not quite, shown a little differently. Basically, in the book, I can just show you with the document camera. It is like that right there. So A is dy by dt when x is equal to 8 and x over t is equal to 10, and dx by dt when x is equal to 1 and dy by dt is equal to negative 6.
okay.
All I did was just organize that information they gave us into a better chart. Okay? Which, if you remember from that list of steps to do related rate problems, is one thing you should get in the habit of doing. Okay? Cleaning things up so that way it's nice and easy to solve. Any questions?
4 8 times 10 is 8. So that's or 5. I can't see.
Of 5.
Oh, 5.
Yes. That's a 5. Okay?
Yeah,
Okay.
I know.
No problem.
It's okay.
Alright. Let's take a look at another one of these. Let's look at an actual related rate problem. One with an actual thing that we're doing. We're going to do 13.
Weirdly.
Okay? 13. Here. Okay? With 13, we've got the radius of a circle. Okay? Basically, is increasing at a rate of 4 centimeters per minute. Find the rates of change of the area when first the radius is equal to 8 centimeters, and then when the radius is equal to 32 centimeters. Now, I'm going to have you guys tell me what to do here. What should be the first thing we do? Draw a diagram. Draw the actual picture here. Good. Okay? Basically, we have a circle at the first time. We'll call it time, doesn't matter. At time 1, who cares? Okay? What time it is. Time doesn't actually matter here. We're just doing it for the sake of our picture. Looks like this here. Its radius is 8, and, well, actually, since we're doing it different radiuses, we'll leave that off. Here's a circle of R, and then at some later time, it's a bigger circle, okay, with R, and the change in R here is going to be 4 centimeters per minute, okay? And we're going to do it once when R starts off being 8, and then once when R is 32, okay? So for A, R is equal to 8, and for B, 8 centimeters, R is equal to 32 centimeters, okay? All right, so now we got our diagram, okay? We got a circle, starting off small, getting bigger, okay? What we want is a change in area. So what do I need to write up here? Next. So the equation that links all this together, right? Okay, so that equation is area is equal to pi r squared, okay? And so is it area that we want? We want instead change in area, so what do I need to do to this equation? Take the derivative with respect to time. So what's the derivative of A?
One.
2 pi
Well, it's a
r.
constant, so there no time.
Okay, it's derivative of A is 1 times dA by dt. So it's just dA by dt. It's what we're after. Okay, pi is a constant, right? So it just stays as pi. Times r squared. What's the derivative of r squared? 2r. It's just 2r times dr by dt. Good. Okay. Basically, one thing to remember here, and this is something that will help you with all these implicit differentiation problems, is when you're doing the derivative of something, okay, it works the normal way a derivative always works. Okay. So r squared, if I differentiate it, it's a power rule, it becomes 2r. Okay. The only difference is because we're not doing it with respect to r, we're doing it with respect to time. We throw on a dr by dt to account for that. Okay. And that's the case that works for every single one of these things. Okay. We saw it with regular implicit differentiation, where we're doing derivatives of y with respect to x. We saw it in the previous problem when we did x and y and differentiated it with respect to time. You know, just think of the normal rules and just realize anytime I take one of those derivatives, just tag on the dr by dt, or the dh by dt, or the dv by dt. Okay? Everyone see that?
Yeah.
All right. So that's all we did here. Now, do we have all the pieces we need? I need r, got r for either case, and dr by dt, got that. So I should be able to put all the pieces in, right? Solve directly. So, for our first option here, for A, when r is 8 centimeters, dA by dt is going to be equal to pi times 2 times 8 centimeters times 4 centimeters per minute. What's that all come out to be? Well, it will be when we're done, but what's 2 times 8 times 4? 64. So it's 64 pi centimeters squared per minute. Okay? Fairly straightforward, right? Is part B on this going to work any differently? No, the only difference is, so of 8, it's 32, and so our answer is bigger. Okay? It ends up being 256 centimeters squared per minute. Okay? That's how the volume, that's how the area changes. Okay? Any questions about how that works? Pretty straightforward, right? Okay, good. All right. Now, in the next 15 minutes, or last 15 minutes of class, what we're going to do is we're going to look at a problem that I'm making up. Okay? And this is to help you guys. This is going to be a much more difficult problem. Okay? But it's one that I've made up that demonstrates how all the different problems that can arise when you're looking at a related rates problem. Okay? So, my problem is going to be as such, okay? A conical water tank, water with an R now, and one R in water.
That says conical?
Yep, conical water tank, okay, is filling up with water, okay? It's flood, okay? Basically, when the radius is 4 meters, and the height is 10 meters, okay? The change in height or I should say depth. Let's use the word depth here. The change in depth is 1/2 meter per minute. Okay? What is the change in volume? Okay? Alright, so that's my problem here. Now, whenever we have one of these problems, what should we always do first?
Sketch.
Sketch a picture of what's going on. Okay? So it's a conical water tank. Okay? For simplicity's sake, we're going to draw it upside down. Okay? Alright? There's water in it at a certain moment in time. We can think of that water as being its own little cone of water in here. Okay? The radius of that water is 4 meters, and the depth of the water at this moment is 10 meters. Okay? And the depth is changing at 1/2 meter per minute.
So that's
Okay.
dt over d.
Okay.
d.
Not dt, but dh by
over
dt.
dt.
Okay, so we can think of this as being dh by dt. Good. Okay. So what I'm also going to do here, in addition to doing this, I'm going to make myself a list of everything I'm given. Okay. R is equal to 4 meters. Okay. H is, or yeah, we'll use H for this, is 10 meters. Okay. The change in H with respect to time is 1/2 meter per minute. Okay? What do we want? It's the only thing that's left up there at the top. Okay, from the proof. dV by dt, right? So we want, this is given, and we want dV by dt. Okay? Alright, so that's everything I'm given, and that's what I want. Now what do I need to do?
What's the equation for volume?
Write the equation of volume, right? It's cone. Who remembers what that equation is?
Are we gonna have to know the equations?
Yes. Okay, it's 1/3 pi r squared h. That's also why at the very beginning of the year, I gave you a sheet with all of them on it.
Is that on the canvas?
Should be on the canvas, yes. Okay, but as someone pointed out correctly, volume is equal to 1/3 pi r squared times h. Okay? Any questions about that there? Alright, so this should be a simple, as simply as just differentiating this, right? Well, we're going to run into a problem right now if we differentiate it as it's written. Let's go ahead and differentiate it. What's the derivative of volume?
dV.
So it's going to be dV over dt, okay, is equal to 1/3 pi. I'm just going to write that as a constant up front. What rule am I going to use for that? Product rule. So it's going to be r squared times the derivative of h plus 2r times the derivative of r times h, right?
We don't have dr over dt.
Ah, someone figured it out. We don't have dr by dt, do we? Okay. So that means we're going to have to figure out some way to get rid of that. Which probably means we're going to have to get rid of r somehow in the original equation, right? Because as it currently stands, we have no clue what the change of rate of the radius is going to be. We don't have that. Can't figure that out yet. Okay? So, how do you think I can get rid of r, the original equation? Okay? Well, take a look at this. What do we know about a cone? A right cone specifically.
It's a triangle.
It's a triangle, right? I could think of there actually being a triangle here, okay? With one leg being 4 and the other leg being 10, okay? As it changes though, okay, as the water fills up, I'm going to have a new H and a new R, right? But what proportion would that new H and new R have? It'd be the same, right? Okay, because they would be similar triangles here. So I can use that fact to actually solve for R in terms of H. I could come through here and say, okay, as a secondary equation, okay, I could say, kind of, secondary, I could say, okay, 4 is to 10 as R is to H, or H, right? Can't I say that? Certainly. I cross multiply here to get 4H is equal to 10R. So then what's R going to be equal to? 4/10 of whatever H is. Okay? So, that gets rid of R, doesn't it? Okay? That means I can replace the R in the original equation with 4/10 of H. Okay? So if we do that, okay, we come through here and rewrite this, it would be V is equal to 1/3 pi times 4/10 h squared times h. We clean that up. If we actually square out 4/10 h, we would get V is equal to 1/3 pi times 16 over 100
Why don't you use two
h
fifths?
squared times h. I could use 2/5.
Okay.
I'm going to just leave it as what I've written so far. Okay? You're absolutely right. I could make it 2/5. Okay? And then finally, this whole thing would clean up to be V is equal to 16 pi over 300 h cubed. Right? Because h squared times h is h cubed. Which now means I have a different equation, a different one to differentiate. Instead of using that one, I'm now going to use this one right here and make dv by dt equal to 16 pi over 300 times 3h squared times dh by dt. And I have all those pieces, don't I?
Yes.
Okay? So now I can just go through and actually solve for dv by dt.
Wait, can you just, well, I'm trying to figure
Oh.
out. So the equation in the blue you crossed out,
Uh-huh.
that was the derivative of the volume equation?
That was the original derivative of volume, but it's the one we couldn't use because we had a dr by dt in it that we don't have. Okay? And-
Well, why are you doing, where did the h come in to that derivative there? Like the dh over dt?
dh over dt right here?
Yeah.
Oh, product rule, right?
Yes.
Take derivative, keep the first one the same, r squared,
Okay.
times derivative of the second.
Derivative plus derivative first times the same.
Yeah.
Okay.
And because we ended up with that, because when we used that rule, we ended up with something we didn't have.
So you're using that same product rule right there in the red above under red.
So, yeah, basically, this, what's in red here, okay, is basically what we've done was when we figured out that we had something we couldn't, when we had something in our equation that we don't actually have the value for, we said we have to get rid of it somehow. And how we're getting rid of it is by basically going back to the original and saying, okay, how can we get rid of r? And one way we can get rid of r is by
Putting it
using,
in terms of h.
yeah, writing in terms of h.
So from v equals 16 pi over 300 h cubed,
Uh-huh.
you use the product rule to get that.
Oh yeah, to get this one right here, yes.
So why is there the dh over dt on the end there? What is that?
Well, what's the derivative of h cubed?
3h squared.
3h squared times dh by dt.
That's what I'm getting confused.
Okay. Every time, remember, this is nothing more than implicit differentiation. Basically, anytime you take the derivative of anything, when you're doing things implicitly like this, you always tag on to the end of it a d of whatever over dt, as is the case here, okay? So, because we're doing the derivative of h, but we're doing still with respect to time, h, the derivative of h cubed becomes 3h squared, you're absolutely right, times dh by dt.
Just tag that on. Right?
You just always tag, yeah, just get used to tagging that on, okay? And this works when we do things implicitly. Normal differentiation, we don't care. We wouldn't do that, okay? But because we're doing it implicitly, we're adding it on, okay? That's why that's there, okay? And so, now it's just a matter of putting in numbers, which we've got all the numbers for this. dv over dt is equal to 16 pi over 300 times 3 times 10 centimeters squared times 1/2 centimeter per minute.
Thought it was meters.
Okay. Oh, yeah, meter, sorry. I switched things up. I got two of these backwards. Meter and then, thank you. Meters and meters. Well, hey, that's nifty, right? 3 times 10 squared is what?
300.
So what's going to happen here?
Don't cancel.
They're going to cancel, okay? What's my 16 and my 1/2 going to do?
18
Give me
pi.
8, right? 8 pi. And then I've got meters squared times meters per minute, which gives me meters cubed per minute. So my change in volume with respect to time is 8 pi, okay, meters cubed per minute. So this thing is just gushing with water. Water's flowing into this thing like crazy, okay? Because that's a lot of water. Okay.
The
You're looking at like 25, 26 cubic meters of water per minute flowing into this thing,
Do we,
okay?
That would fill up a pool.
are you talking about cube?
Did you take?
Okay.
Did you take the derivative of what is it? Did you do the quotient rule for the volume?
For the volume,
Yeah.
right here,
Yeah.
well, it's just volume, right?
But
Derivative of volume is just 1 dV by dt, right?
but then it turns into v equals 16.
Right over here?
Is it, oh, never mind. Yeah, sorry.
Yeah, it's not,
My bad.
yeah, okay.
I don't know what those. I was thinking you need to do like a double.
Oh, no. Okay. Now, why is it meters cubed?
Yeah.
How do I get the
So
meters
dumb.
cubed there? Okay, well, if I follow my units here, I had 10 meters squared. Okay, so I had 10 meters, parentheses squared, so that's where I get the meters squared from. And I started with meters per minute. So meters squared times meters per minute is meters cubed per minute.
So this could likely be a test problem.
This could be, yes, something like this. Remember, you guys have a quiz on Wednesday. It's an AP style question you're going to do in class. Okay?
Are we doing practice of it yet? Have we done practice of it?
This is basically the practice of it right here.
Okay.
Okay? Got it? And there's some notes online. There's several examples online, things like that. Okay? On campus. All right. Any questions about how these work? This, by the way, is about as hard as they get. Okay? So don't sweat it at this point. This is about the toughest it's going to be. All right, everybody.